So this unit is about we call curve sketching. So we're going to be using the derivative and the second derivative to gather information about how the graph is behaving in terms of when it's rising, when it's falling, and different the curvature of the graph. Our derivative process is not going to feel any different. A lot of times, all we need is power rule to get to the derivative. It's just interpreting that in different contexts here. So let me just highlight notes here on the first page. So first is the definition involving max and mins. So anytime there's a hill or valley of the graph, we consider that a relative maximum or a relative minimum. Or you can sometimes see the word local max and local min. Relative and local just means that this is the maximum point for its immediate region. So if we're comparing points to the left and to the right, it is higher than any point in this local region. Here, it's considered relative minimum because it's within this region, it is the lowest point. And then this is also relative max because within this region, it's also the highest point. But this point is considered a relative max because relative to it is a hill of the graph, but it's also an absolute maximum because why? Yes. Overall, it's the highest point. No, there's no other point higher than that. So we also consider that an absolute maximum. This graph has no absolute minimum because it would need to be a physical point in order to be an absolute minimum. Like negative infinity would not be considered an absolute minimum because it's not a physical point. So absolute max, absolute min has to be a physical highest or lowest point on the graph. And because of the arrows, we're not able to locate a specific value that's the lowest point overall. Okay, if I have a closed interval here, closed interval is where your endpoints are nicely defined and it doesn't continue to negative or positive infinity. This graph does have a relative minimum because in this region, it's the lowest point. It's also an absolute minimum because overall, this is the lowest point. This is only considered an absolute max because it is higher than the points around it, but it is not a hill of a graph. It needs to have points on either side in order for it to be considered a relative maximum. I know that AP Pre-Calc may have to find it a little differently, but then in this class, we consider relative maximum to be, we need to have something to compare with on both sides in order for it to call it a relative max. So this is an absolute max, but not a relative maximum. Okay, so this is open interval. So open interval means that there are holes that are at the ends here. So the holes indicate that we can get infinitely close towards these points, but we'll never be able to reach that point. It will just get infinitely closer. There's a hole. So this graph does still have a relative minimum and an absolute minimum. That is still true. But this one has no absolute max, nor a relative max. No absolute max because we can't physically pinpoint a specific number that's the highest overall. So if I pick a point really, really close to that hole, I can always pick a point even closer. So we can get infinitely close towards that point. So therefore, we can't pinpoint a value that's therefore no absolute maximum. So today we're going to focus on something what we call extreme value theorem. So extreme value theorem is we're just trying to find the highest and lowest points on the graph. Now, obviously, if the graph is in front of you, it'll be easy because you can just look at the graph and tell what the highest and lowest points are. We're doing this without the graph and just relying on the function and relying on derivative. So here's extreme value theorem. Extreme value theorem says if a function is continuous on the closed interval, so there can't be any holes, there can't be any breaks. As long as we can establish that there are no breaks on the interval, then the graph has both an absolute max and an absolute minimum on that interval. So the way that we're going to determine the max and mins without looking at the graph is we're going to be finding critical values and testing endpoints. So critical values are going to come from the derivative. We're going to set the derivative equal to 0, both the numerator and the denominator separately. And then after we find our candidates, we're going to take those and the endpoints, plug them into the original function, and compare the y values. So let me just show you a graph that kind of highlights the points that we need to consider. So let's say a graph looked like this. The only candidates that can end up being an absolute max or absolute min are your endpoints, right? You can imagine endpoints being the highest and lowest points. And then also places where there's a slope 0 or slope undefined. These are the only candidates that can ever end up being the highest or lowest on the graph. So that's why we only have to worry about these points. So we'll have to worry about the endpoints and the critical points. So critical points comes from the derivative. Endpoints will always be given to you at the beginning of the problem. And then all we're doing is after we identify these candidates, then we're just plugging them into the original function and then comparing the y values. Highest y value will be your absolute max. Lowest will be your absolute min. All right, let's go to page 2. The first step is we want to confirm that our graph is continuous on a closed interval. The nice thing is if it's a polynomial, then you can just go ahead and make that statement. There's nothing to check. But if there is a hole or an asymptote, basically if there's a variable in the denominator, we're going to have to be a little bit more careful and see if, is that asymptote or hole going to impact my interval? If it impacts the interval, then we have to stop and say extreme value theorem doesn't apply. But if it does not interfere with the interval, then we continue with our process. So we first have to establish our function is continuous. Then we're going to look for our candidates. We already have 2 candidates at the beginning of the problem. We're always going to have endpoints provided for us, so we know we're going to test them. But to find critical points, any additional candidates, we're going to look at it from the derivative level. So we're going to find f prime, set f prime equal to 0. Sometimes f prime has both the numerator and denominator. If that's the case, we're going to set both the numerator and the denominator equal to 0 separately, and then see if they land inside the interval for us to test. Okay, after we find our candidates from our critical points, we're going to place them and the endpoints back into the original function, and then just compare the y values. This unit, you'll also get to use a calculator. All right, let's go through example 1 so you can see the full process for these problems. So it says, what are the absolute extrema? We're trying to find the highest and lowest y values on the graph. F of x is 3x to the 4th minus 4x cubed. Are there any issues with this graph? Any holes, any asymptotes? Okay, this one is safe, right? This is a polynomial. It's going to be a smooth curve. There's no variable in the denominator. We're good. But we have to make sure that we practice writing out our justification, just like intermediate value theorem. I had you guys write out your condition as part of earning credit for the problem. So let's go ahead and state that. Our function is continuous. On the closed interval from 0 to 2. Even though it's continuous everywhere, we have to state our condition is for the interval, so we have to make sure we include the interval in our statement. Okay, next up, we're going to look for candidates to test. We already have 2 candidates, so we know we're going to test them at the end. We're now looking for any additional candidates that comes from the derivative. So we're going to set f prime equal to 0 and look for places where either a slope is 0 or slope is undefined. Slope 0 doesn't guarantee a max or min, but it is a place to look, right? Anytime there's a slope 0, we know that is a potential place where the graph is peaking or where it's valleying. Okay, so let's find f prime. Derivative, power rule, 3x to the fourth becomes 12x cubed minus, yeah. There is no denominator to worry about, so we're just going to set the numerator equal to 0. Factor, GCF. What can we take out? 12x squared. Take 12x squared. And we're left with x minus 1. All right, we have two candidates, right? If I set 12x squared equals 0 and x minus 1 equal to 0, I'll find two critical points. X equals 0 if I divide by 12 and take the square root, and x equals 1. All right, anytime we find critical points, we always have to consider the location of these critical points. Are both of these valid for us to test? Yes, 0 is a duplicate, so I mean, we're going to test 0 anyways. It shows up again. But 1 is valid because 1 is between the two endpoints. So sometimes you may go through this full process and not get any critical points that land inside the interval, and that's okay. If you don't get any additional candidates, that means you only have to test 2. All right, so now we're just looking to see at these candidate points what's the highest and lowest y values. So we're going to plug them all back into the original function. So 0, and for x of the original function, 0 minus 0 is 0. Plug 1 into the function, 3 minus 4 is -1. Plug 2 into the function. I get 48 minus 32, which is 16. All right, what's the highest y value that you see? That's my absolute max. Lowest y value, -1, that's my absolute min. So I just want us to do this where finding absolute max, absolute min, I just want the y values. So just give me the y values, don't give me the x values. So we're going to say absolute max value is 16. Absolute min value is -1. The x value doesn't matter, so we're going to stay away from the x values. Just give me the y values. So again, to recap the steps, you always want to make sure you can provide your condition statement. Second, you're going to find the derivative, clean up the derivative, set both the numerator and denominator equal to 0 if there's a denominator. And then once you find your potential candidates, make sure that they're inside the interval. If they're inside the interval, they can keep it. If they're not, we're not going to use it. Take any valid critical points and endpoints, put them into the original function, and then just give me the highest and lowest y values. Okay. That's all we're going to do today. And then we'll do a couple practice problems and we'll go back to quiz review. All right, let's look at example 2. F of x equals x minus 1 to the, sorry, it's hard to read. It's 2/3. X minus 1 raised to the 2/3. First off, it's cubic root, so we don't have to worry about any issues with values that are going to cause, that are not going to fall within the domain. Also, we don't see any denominators, so there's no holes, there's no asymptote, so we're safe. This function is safe. We can just go ahead and jump into our continuity statement. Okay, what's next? Find the what? Derivative, yeah. We already know we're going to test -1 and 0, so we're saving that to the end. We're going to look for any additional candidates that could be part of our problem. So let's find f prime. What rule do you have to go through, though, to get the derivative? Chain, yeah. So outside times inside derivative. So outside, we're just focusing on the parentheses. So bring down the 2/3, keep the x minus 1, subtract 1 from the exponent. That's the outside. Times what? 1. Yeah. So we look for the inside. Nothing additional will come out, but I'm just going to put a 1 there as a reminder. We did apply the full chain rule. All right, let's clean this up so that it'll be easier to interpret. Remember, critical points can come from both numerator and denominator, so it's okay to just have everything split up. So I'm going to put the 2 above, the 3 below, the x minus 1. I'm also going to put that below as well. We have a fraction for the derivative, and we're going to look at both places. Is there anything that's going to come from the numerator? Right. If I set 2 equal to 0, there's no variable there, so I can ignore it. The denominator, I am going to find a critical point, so set that equal to 0. Divide by 3, cube both sides, solve for x. X equals what? Yeah. I'll just go through the steps here. All right, so there's my critical point. Is this a valid critical point? No, it's not inside the interval. If it's not inside the interval, it's not part of our problem. There is no critical point for us to test, but we can still move forward. We just have 2 points to test. We only have to worry about these 2 points. So now what's next? Get into the original. Right. So we know 1 will have to be the higher, 1 will be the lower. So 1 will be the max, the other will be the min. Negative 2 to the 2/3. I'm going to take care of the squared first. Negative 2 squared is 4. So this is going to be the cube root of 4, which is something like 1.2 or something like that. All right, next up, f of 0. Um, 0 minus 1 is negative 1. Negative 1 to the 2/3. Negative 1 squared is just positive 1. Cube root of 1 is still 1. So we only have to worry about these 2 points. Okay, so absolute max is cube root of 4. Absolute min value is 1. All right, example 3 is a little messier, so we'll go through this a little bit slower, but same process. First, we're going to look at our function to see if there's any issues. We do have a square root, so we know square roots can't handle every value, right? We want to make sure that there's no negative inside here. But if I plug 0 and 3, we're safe. There's nothing that's going to cause this to be negative. There's no denominator, so our function is safe. It's continuous on the interval, but we just need to make sure we practice writing our condition statement as part of earning credit for the problem. All right, this derivative is a little messier here. If I want to find the derivative, what's involved? Can you tell? There's 2 rules here. Let me write it out this way. What? Good, chain and product. Which one is going to come first? Product, yeah. Chain is only over the second half of the problem because of the parentheses, but product rule is going to see both the 4/3 x and the parentheses. So we always apply the larger rule first. So do product rule. So the derivative is a little messy, and then we have to still do common denominators. So it's a little bit longer problem here. Let me zoom in so you can see all my steps. F is the fourth is x. G prime, this is where chain rule will be applied. Outside times inside's derivative. So outside is parentheses. I'm just doing power rule with the parentheses. 1/2 parentheses to the -1/2. Moving on to the inside, 3 minus x becomes -1. Now we're just looking to clean this up. Just gonna place the numerators together, denominators together. We're gonna have to go through common denominators because it's hard to look for critical points when you have two different fractions. So we're going to find a way to merge them together. But all of this can all go under one denominator. Sorry, one fraction. The negative I'm pulling out in front. The 4 and 2 just becomes 2. And then the 2x over 3. And I'm going to push the negative exponent back to the denominator. So I have two fractions. I want to build a common denominator. My common denominator is going to be the larger of the two. So my common denominator is going to be 3 times 3 minus x to the 1/2. Let me put that in place. Balanced each fraction, the old denominator to new denominator is missing a 3 minus x to the 1/2. So I need to multiply the top by 3 minus x to the 1/2. Which is really just square root. So if I multiply two square roots together, I'm just left with that 3 minus x. So it's just 4 times 3 minus x. It's nice, the square root drops out. Here, my second fraction, I don't have any new changes, so I can keep my original numerator. Okay, so now let's merge it into one fraction so that we can safely set the numerator and denominator equal to 0 to find our critical points. This ends up being 12 minus 4x minus 2x. So 12 minus 4x minus 2x becomes 12 minus 6x. And the denominator is just 3 times 3 minus x to the 1/2. Okay, so now I have a cleaned up version of my derivative. I'm going to set the numerator equal to 0, denominator equal to 0, and see if they are valid candidates. If they are, then I'm going to plug all the valid candidates back into the original function and then compare the y values. Highest will be the absolute max. The lowest is the absolute min. So 12 minus 6x. 6x equals 12. X equals 2. The denominator. Divide by 3, square both sides. X equals 3. All right, are both of these valid candidates? Yes. I got a duplicate. I was going to test 3 anyway, just 3 shows up again. So we only have to worry about 3 unique values, 0, 2, and 3. And where do we put them? Good, original. Now we're looking for the physical locations, physical y values. Okay, if I plug 0, the nice thing about 0 is that 4/3 times 0 is 0. Anything times 0 is 0. So f of 0 is 0. F of 2. 3 minus 2 is 1. Square root of 1 is 1. 4/3 times 2 is just 8/3. And f of 3 is nice because if I plug 3 in, 3 minus 3 is 0. Root 0 is 0. Anything times 0 is just going to be 0. So my absolute max value is what?
2.
Yep, and my absolute min is 0. Yeah, don't worry about the x values. Just give me the y. So absolute max is 8/3. Absolute min is 0. All right, go to page 3. Let's just do 19 and 21, and then we'll go, we'll do some more review. Okay. Right, finding extrema on the closed interval. So first things first, any issues with our condition? Are we safe? Yeah, so write your condition. Next up, you're going to find additional candidates besides the endpoints. So find G prime, set G prime to go to 0, and see if your critical point is a valid one to use. Okay, what you get for your critical point? X equals what? 2, yep. Is 2 valid? Yes, 2 lands between 0 and 6. So we have 3 points to test. So find G of 0, find G of 6, find G of 2, and then make your decision based off of comparing your y values. Okay, try 21 on your own, see if the steps make sense.
Can we like label like much like G of 2 or G of 6? Can we put next to it or next 24 ABS max?
No,
Or do you want us to?
yeah, I really want us to stay away from the x values, just so that sometimes students get thrown off and they want to provide the x value as the max, and I want us to get away from that. So I want us to just emphasize the y value and only the y value. Yeah. All right, try 21. make sure you write your continuous statements. F prime, find your derivative, set equal to 0. Factor 3x out, solve for x. I get 0 and 1. They're both valid, right? 0 is safety between -1 and 2. 1 is also safety between 1 and 2. So now we have 4 points to test. F of 0, f of -1, f of 2, f of 0. They all go back into the original function. And we're just looking at the y values. Highest is your absolute max. Lowest is your absolute min. All right, let's go to your quiz review packet. Go to page 14. Shadow problem. See if you can set this one up on your own. Oh, 6. Sorry. dxdt is the rate of change of the person walking. He's walking away from the lamppost, so dxdt is positive. We put that into the derivative equation. We get 30/9. This is the length of the shadow changing, but the problem is asking for the tip. So we take the length of the shadow changing plus the person walking, add those two rates together, and we get the rate of the tip. Part B, find the rate of change of the large area. All right, so formula for area is 1/2 base times height. What's the base? X plus Y. What's the height? 15. All right, do we need product rule here? I think we only need product rule if you have a variable multiplied with another variable. Here I have I mean, we could, but we don't have to because it's just a coefficient, right? I think power rule should be enough. So I'm going to distribute that 15/2 through. There's no need for product rule because I can just do dx dt plus dy dt and dA dt. So this one doesn't need product rule. Area is square feet, times is seconds. So square feet per second. Let's not worry about the next one here. Let's look at 6 and 7. So 6 is a limit problem. What's the first thing we do with limit? Yeah, direct substitution. So we'll try number 6. Okay, if we get 0, 0, that allows us to do what? L'Hopital's row. So take the derivative of the top, derivative of the bottom, and then reevaluate. If you get a real number, you can stop. If you get a 0/0, you can do L'Hopital's rule again. Okay, next one. Use this as your starting function, linear approximation. So we're going to find our order pair. We're going to find our slope, point slope form, and then we can plug in the 8.04. What x value do we want to choose to build our tangent line around? X, yeah, x equals 8. So plug in, find your order pair, get this function ready for the derivative, find the derivative, plug in 8 to get the slope, point slope form. Most of your effort is just trying to get your tangent line equation, and at the very end, you can plug in 8.04 as your decimal. Okay, once you have your tangent line equation, then plug that decimal in for x, and that's your final step. Okay, page 17. Let's do the cone problem, number 2. Okay, does anybody still need to look at the linear approximation problem? Sorry, number 2 on page 17. I see a lot of students wanting to do the derivative at this stage, but we're not ready for the derivative yet, at least not relying on just power rules. So spend the time. You got to get your h's to come together, get your coefficients to come together. If you only see one H on the right side, then that's when you know you're ready for power rule. All right, we're saving that 4 until the end. But now that we have a derivative, everything is ready to be plugged in. So I can plug in 3/5 in for dVdt. I can plug 4 in for H. And now I'm just trying to figure out how to get that dHdt value.
Mr. Yang, where did you get the 4 from?
It says, what rate is the depth of water changing when the tank is half full?
Oh, okay.
So because the height is 8, half, which is 8. Careful that your pi is going to end up in the denominator. So when everything is said and done, make sure your pi is still in the denominator.
It's just
Oh.
1,200.
I messed up somewhere here.
I think it's supposed to be 6,000.
Yeah, I think you're right. Yeah, sorry, 1,200. Thanks.
And we're just.
Okay, no homework this weekend. We're going to do 5.2 and then we'll continue practicing. Okay, quiz on Tuesday. Have a great weekend, guys.
Yeah.
Thank
Love
you,
sharing.
Mr.
Have a
Yang.
weekend. Thank you.
Thank you.
Bye. Okay.
Not forgetting. Mr. Yang, not
Have a good
forgetting.
weekend.
I thought this was. No. Exit call. Take that and.
Have a good weekend. Thank you.
Did you see the disrespect that just happened? Just took my drink and then finished it and then threw it away.
Oh, no.
Okay. Gonna quote unquote accidentally spill his drink. Not forgetting my camera. I'm not gonna do it.
think someone took it already.
He took it too. He drank my drink, threw it away, and then took my camera. Thank you, Mr. Yang.
Hey, guys.